Today we're going to explore a number known as Liouville's constant. And what makes this number very interesting is it is one of the earliest known transcendental numbers. In other words, it's one of the numbers that was first proven to be transcendental. So let's see the definition of this number. So we'll call it L, and it's defined to be 1 over 10 to the 1 factorial plus 1 over 10 to the 2 factorial plus 1 over 10 to the 3 factorial plus 1 over 10 to the 4 factorial, and so on and so forth. So we could write that as the sum as n goes from 1 to infinity of 1 over 10 to the n factorial. And the first couple digits look like this. We have 0.110001, 000, well, we've got a bunch more zeros and then a 1, and then so on and so forth. So notice that we have a 1 at the n factorial digit for all n. So there's the 1 factorial digit, the 2 factorial digit, there's the 3 factorial or 6 digit, and so on and so forth. Okay, so we've got one other thing that we want to define right off the bat, and that is the notion of a Liouville number. And we say that a real number alpha is a Liouville number if for all natural numbers n, we can find integers a and b, where b is bigger than 1, such that the absolute value of alpha minus a over b is strictly between 0 and 1 over b to the n. So we've got this notion of a Liouville number and then Liouville's constant. Now, it wouldn't make sense for both of those to have the same kind of name unless Liouville's constant was a Liouville number. So that's the first thing that we'll prove, that L is a Liouville number. Okay, so note over here in the definition of a Liouville number, we have to have something holding for all natural numbers n. So that means we need to be given an arbitrary natural number n and then somehow construct this a and b. Okay, so let's do that. So let's say we are given some natural number n. Let's write L as follows. So we can write L as a over 10 to the n factorial plus the sum as n, or maybe as m, goes from n plus 1 up to infinity of 1 over 10 to the m factorial. Okay, so you might say, well, what is this number a? Well, this number a is just kind of whatever integer it takes to collapse the first n terms into a single fraction. So in other words, we have a over 10 to the n factorial is the same thing as the sum as m goes from 1 to n of 1 over 10 to the m factorial, all collapsed into a single fraction. So this a is going to play the role of the a over here, and then this 10 to the n factorial will play the role of this b over here. So that means we need to calculate this difference, L minus a over b, for this setup. So let's do that. We've got L minus a over b. So notice that that is clearly bigger than 0. It's clearly bigger than 0 because that gives us this tail right here. In fact, we know exactly what this is. So that's going to be the sum as m goes from n plus 1 up to infinity of 1 over 10 to the m factorial. That's just from subtracting off like this thing right here, like I just said. Okay, now let's take out the first term. So that's going to be 1 over 10 to the n plus 1 factorial plus, now we have the sum as m goes from n plus 2 up to infinity of 1 over 10 to the m factorial. Like I said, that's taking the first term out of this kind of remainder sum right here. Okay, so now I'm going to introduce an inequality. So this is most definitely less than 1 over 10 to the n plus 1 factorial. So we will not change that first term. And then we'll replace this second term with plus 1 over 10 to the n plus 1 factorial times the sum as m goes from 1 up to infinity of 1 over 2 to the m. So how did this inequality come into existence? Well, let's notice that if we move this 10 to the n plus 1 factorial inside, and compare every denominator here with every denominator above, every denominator down here is smaller because I've replaced most of the 10s with 2s, and actually a lot of the 10s with only 1s. So if I have a smaller denominator, I have a larger overall object. Now, furthermore, this guy right here, which I'll box in red, is a geometric series, and we can easily calculate the sum of a geometric series. So it's the first term, which is a half, over 1 minus the common ratio, which is also a half, so that gives us 1. So now we can add these two things together. That'll give us 2 over 10 to the n plus 1 factorial, like that. But that's going to be less than 10 over 10 to the n plus 1 factorial. There I just replaced the numerator, which was 2, with a numerator of 10. That obviously gives us something larger. But now that's going to be less than 1 over 10 to the n factorial, all to the n power. And so that's by some simplification that you could do. I'll leave that step maybe for a homework exercise. So anyway, notice that since the role of B here is being played by this guy right here, we have that our absolute value of L minus A over B is less than 1 over B to the n as needed to satisfy this definition of a Liouville number. So that means we've shown that Liouville's constant is a Liouville number. Now we can move on towards showing that all Liouville numbers are transcendental, and thus Liouville's constant is also transcendental. As promised, now we're going to prove that all Liouville numbers are transcendental. Let's quickly recall that being transcendental means that you are not the root of a polynomial with integer coefficients. So we'll start by proving that all Liouville numbers are irrational, and then use that in order to prove that they're all transcendental. Okay, so let's suppose that we have alpha is a Liouville number. So I'll shorten it like that. And by way of contradiction, let's also suppose that alpha is a rational number. So like I said, we should end up with some sort of contradiction. Note that means that alpha is equal to P over Q, where P and Q are integers. We can take P to be any integer, and then we'll take Q to be a positive integer. In other words, a natural number. Okay, so next, let's take a new natural number, which I'll call n, satisfying the following rule. So we'll have 2 to the n minus 1 is bigger than q. So that's always possible. For any rational number, for any natural number q, we can always find a power of 2 larger than that natural number. Okay, so next, let's take any numbers a and b. So these are integers. Maybe b is a natural number just like q was, such that p over q is not the same thing as a over b. So that means this ratio is different than this ratio. Okay, so now let's do our calculation. So thus, we have the absolute value of alpha minus a over b. So that's going to be equal to the absolute value of p over q minus a over b, like that. But then, just by doing fraction arithmetic, that's going to be the absolute value of PB minus AQ over BQ. But then, since P over Q is not equal to A over B, then that means this thing here, which I'm putting in green parentheses, is not equal to 0. So that means when we take its absolute value, it'll be bigger than or equal to 1. So that means this whole thing is bigger than or equal to 1 over the denominator. Okay, but now note that we chose n satisfying this inequality right here with 2 to the n. But now this is bigger than 1 over 2 to the n minus 1 times b. But let's recall that we take b to be bigger than or equal to 2 by this condition. But if b is bigger than or equal to 2, that makes this thing bigger than 1 over b to the n, because we're replacing the denominator with something larger. Okay, so now let's look at the extreme left and right-hand side of what we've gotten. We've gotten this difference between alpha, our supposed Liouville number, and this fraction is bigger than 1 over b to the n. But then that kind of thing can be constructed for this special choice of natural number satisfying this inequality. But that means that the definition for a Liouville number is not satisfied. So in other words, we have alpha is not a Liouville number, which is our contradiction. And thus, we are contradicting this assumption right here that alpha is rational. So we have alpha is indeed irrational. Okay, now we've got alpha is irrational. Let's move on to prove that it is transcendental. So we've got alpha, which is a Liouville number. We just showed that it is not rational. In other words, it's irrational. Now we want to show it's transcendental. And we're going to do this by way of contradiction again. So by way of contradiction, let's suppose alpha is the root of a polynomial. So let's call that polynomial f of x. And maybe we would say that f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a naught, where we can take those a's as integers. So in other words, we have f of x is in the integers adjoin x. So that's just the definition of a non-transcendental or a algebraic number. Okay, so let's maybe reiterate the fact that we have f evaluated at alpha is equal to 0. That's what it means to be a root. Okay, so now we're going to introduce some more numbers. So let's say that m is equal to the maximum of f prime of x. So we know that f prime will attain a maximum just by the extreme value theorem applied to f prime. Since f is a polynomial, f prime is a polynomial, and thus it's well behaved. And that maximum occurs on the interval, or we'll take that maximum on the interval from alpha minus 1 to alpha plus 1. Okay, so another thing that we want to do is take alpha 1 up to alpha m to be distinct roots of f of x not equal to alpha. So we know that f of x has a root of alpha, but it might have some more roots. So let's say that those are the other roots, but those are all different. So next, let's take the number a to be less than the minimum of the numbers from the following set. So we've got the number 1 over m, and then the distance between alpha and alpha 1, the distance between alpha and alpha 2, all the way up to the distance between alpha and alpha m. So we know that none of those are equal to 0, so we can take definitely a to be bigger than 0. So that's important to notice as well. Okay, we've got one more number to introduce. So that last number we'll call r, and r will be a natural number such that 2 to the r is bigger than or equal to 1 over a. So let's box all of these things that we've just created. So we've created this number m, we've just created this number a, and we've created this number r, so they satisfy all of those rules right there. So next, we know that alpha is a Liouville number. So that means for any natural number, the natural number that we'll take will be n plus r. We can find integers a and b, where b is bigger than 1, where we have this condition satisfied. Okay, so let's do that. Let's find integers a and b bigger than 1, such that we have the absolute value of alpha minus a over b is less than 1 over b to the n plus r. But now that's going to be less than or equal to 1 over 2 to the r times b to the n. That's because since b is bigger than 1, it is bigger than or equal to 2, and that's how that inequality will shake up. But let's look at how we chose r here. We chose r so that 2 to the r was bigger than or equal to 1 over a. That makes this whole thing less than or equal to a over b to the n. But now, since b is bigger than 1, that means this whole thing is less than a. But note that a was chosen to satisfy this inequality. That tells us that this whole thing is less than the minimum of 1 and alpha minus alpha 1 all the way down to alpha minus alpha m. So now this strict inequality tells us that this absolute value is never equal to any of these absolute values. So that's important. And it also tells us that this absolute value is less than 1. So that gives us 2 pieces of information, which I'll write right here, but then I'm kind of running out of room, so I'll move to the top. So those 2 pieces of information are alpha and beta, come from the interval alpha minus 1 to alpha plus 1. That's from this inequality being less than 1. And also, we know that a over b is not equal to alpha I for all I. And that's from this inequality being strictly less than all of these differences over here. Okay, so let's bring the necessary information to the top and we'll finish it off. So I won't reiterate everything that we did so far, but remember that alpha was a root of a polynomial. That's also our Liouville number, so we want to somehow get to a contradiction, because it being the root of a polynomial means it's not transcendental, which is not what we're trying to prove. Then we had a over b, where we constructed a and b are between alpha minus 1 and alpha plus 1, and then a over b were not roots of the polynomial. So again, that was from our construction of a and b. So next we're going to use some calculus. So by the mean value theorem, so remember that the mean value theorem says that at some point the average rate of change is equal to the instantaneous rate of change. So it's a pretty interesting result. If you've taken a calculus class, you should be very familiar with the mean value theorem. So there exists an x naught, and it is between alpha and a over b, satisfying the following condition. So we have f prime evaluated at x naught, so that's the instantaneous rate of change, is equal to f of alpha minus f of a over b over alpha minus a over b. So that's the average rate of change. Okay, so next up, let's notice that f of alpha is equal to 0 by our assumption, which is right here. And then we can move some things around, and moving things around gives us the absolute value of alpha minus a over b is equal to the absolute value of f of a over b. Remember, that's not equal to 0 by the fact that a over b can't be a root of our polynomial. Remember, those are the roots of the polynomial. Over the absolute value of f prime of x naught. But let's recall that m was the absolute value of x naught. So that makes this whole thing bigger than or equal to the absolute value of f of a over b over m. Remember, we defined m on the last board. But then we can actually bound this guy as well. And this guy is bound by 1 over b to the n. So that gives us 1 over b to the n times m. I think we need to explain that a little bit, but we'll get to that just kind of at the end of this whole thing. But then, again, by some of our construction of constants on the last board, we see that this is bigger than a over b to the n. But on the last board, we showed that a over b to the n was bigger than or equal to the absolute value of alpha minus a over b. Okay, so now let's look at this inequality we've constructed. We've got alpha minus a over b is strictly greater than alpha minus a over b, which is a clear contradiction. We've contradicted the assumption that alpha is a root of a polynomial, and thus alpha is not a root of a polynomial. So that leaves us one thing to do, and that's to fill in this little gap right here, but that's actually not that bad. Let's do that over here. I'll put a blue dot to show that we're doing this. So let's take the absolute value of f of a over b. So that's going to be equal to the absolute value of c naught plus c1 a over b plus all the way up to cn a over b, where I know earlier I called the coefficients a subscripts, but now I'll call them c subscripts just so that it's not so confusing. And then from here, we will pull out a b to the n. Sorry, this should be to the n power, just based off of the definition of our polynomial. So that gives us 1 over b to the n times the absolute value of c naught b to the n plus a bunch of other terms, and then finally cn a to the n. But now we know this guy right here is not equal to 0, because if it were equal to 0, then this polynomial would be equal to 0, which we already showed is not possible. And this is an integer, so if it's an integer that's not equal to 0, when we take the absolute value, we get something bigger than or equal to 1. So that means this whole thing is bigger than or equal to 1 over b to the n, which is what we took out. And that fills in this little gap right here. Okay, so as a conclusion, we've shown that all Liouville numbers are transcendental. But a corollary to that, a very quick corollary to that, is that this number called Liouville's constant is also transcendental. And that's a good place to stop.